Hi, I'm Niels, and in this video I'll talk about our paper, The Colored Cut Games. This is joint work with Niels Grüttemeier, Christian Komisewicz, and Frank Sommer. And The Colored Cut Games is a new family of defender-attacker games played on edge-colored graph to model specific aspects of network security analysis. So, why do we consider edge-colored graphs? Let's give a brief motivation. Let this network somehow describe the connection between Germany and India. And some links in this networks can only be traversed with the internet. Some of them can only be traversed or used by taking a walk, by using public transportation, or using a private helicopter. Well, to give this talk right here, I had to play against multiple adversaries. First of all, someone at my university who told me, well, we wouldn't pay you to use a private helicopter, so these links were not possible for me to traverse. On the other hand, due to the corona crisis, using public transportation was also not an option for me, so also these links failed. But luckily, there is still a connection left between Germany and India, namely the internet. So it was possible to give this talk as a pre-recorded video here on YouTube to explain the topic of our paper. And one can now use these edge-colored graphs to model these different types of vulnerabilities of links in a network. In this case, for example, here the public transportation links, all of them failed simultaneously because of the corona crisis, and so they all share the same vulnerability in this case. So even though they are not directly connected, we can model this shared vulnerability with these edge colors. To now measure the robustness or the vulnerability between two specific endpoints in these networks, in this example S&T, one can now define so-called colored ST cuts. And a colored ST cut is a set of colors such that removing all edges colored in any of these colors disconnects S from T. So, in other words, a colored ST cut contains for each ST path at least the color of one of the edges of this path. So, in this example, we can see that, well, let's give a greedy approach to obtain such a colored ST cut by removing green and red, which are the most frequent colors in this network. We still didn't obtain a colored ST cut, since there's still a blue-gray path remaining. So we have to take at least a third color. But actually, there is a colored ST card with only two colors in this network. So if we first of all remove red, and afterwards we can see that there's still this green, black, blue, green, and this blue-gray path remaining. So we only have to cut these two paths, and we can use this just remove the color blue. So with two colors, red and blue, we also obtained a color ST card with two colors in this network. As I mentioned before, a color set is a colored ST card, even only if it contains at least one color for each of the ST paths. So there's a very close relation between these colored ST cards and hitting sets in the following way, that a color set is a colored ST card, even only if it is a hitting set for the collection of color sets of ST paths. And this close relation between hitting sets and colored ST cuts will be used later to obtain positive results. So, such a colored ST cut, or the goal of obtaining such a colored ST cut, can thus be seen as a goal of an attacker who tries to disconnect S&T. So, the corresponding decision problem, called colored ST cut, is then defined as the question if is it possible to obtain a colored ST cut of size at most k. This problem was first introduced in 2002 by Ya et al. And shown to be NP-complete. On the other hand, if one wants to find out if it is possible to connect S&T with as few colors as possible, one can define the labeled path problem, in which we want to know if there is an ST path in a graph with at most k colors. So in this example here, we can see that with the colors red and cyan, we are able to connect S and T. So by securing only two vulnerabilities of our network, we are able to establish an unbreakable link between these endpoints. This labeled path problem was introduced in 2000 and also shown to be NP-complete. And both the colored ST-cut and the labeled path problems were well analyzed in the last 20 years. So, in our paper, we introduced the colored cut games, where a defender and an attacker play against each other. And I'll first show these games on an example graph, this one here, before I go to the actual definition. So let's say we have this graph, and we play a defender against an attacker. Each of these agents is allowed to choose one color at a turn, and players are not allowed to choose previously chosen colors. So we start with defender, and he's allowed to choose one color. His goal is to connect S with T, so he should choose the red color. As otherwise, if the attacker chooses this color, then the attacker obtains an ST cut, a colored ST cut, and so the defender would lose the game. So the defender chooses red. He secures these colors, all edges colored in red. Now it's the attacker's turn, and the attacker tries to disconnect S and T, and since the defender already secured a path from S to this point here, and this point is adjacent to T, the attacker has to choose blue, as otherwise the defender can complete an ST path with the colors blue and red. So the attacker chooses blue, and let's say we remove these colors from the graph. Now it's again the defender's turn, and we can see that if the defender now chooses green, he can secure a pass between S and T with the colors red and green and win the game.
This was just an example for the colored cut games. In general, they are defined in the following way, that they generalize both the colored ST cut and the labeled path problem. And to do so, we have budgets for each of the turns of the agents. And so the defender is allowed to choose DJ many colors in his J's turn, and the attacker is allowed to choose AJ many colors in his J's turn. And these two players play in an alternating fashion. They choose colors in each of their turns, and they are not allowed to choose previously chosen colors. And the goal of the attacker is to complete a colored ST cut.
So first in our paper, we analyzed the complexity of the color cut games, and we were able to show that if the number of turns is not a constant, then these color cut games are piece-based complete, even if the budget in each turn is equal to 1. So if the defender and the attacker are both only allowed to choose one color at a time. On the other hand, we were able to show that if the number of turns is a fixed constant, then the colored cut games are complete for the 2ith level of the polynomial time hierarchy, even if we have a graph with a constant maximum degree. But don't worry, our paper does not only contain negative results, we will also obtain positive results, namely polynomial kernelization algorithms for all colored cut games. And first of all, I should explain what is a polynomial kernelization algorithm. Such an algorithm runs in polynomial time and transforms an instance of colored cut games in the parameter p into another instance of colored cut games in the parameter p prime, such that I and I prime are equivalent instances. So the defender has a winning strategy in I if and only if the defender has a winning strategy in I prime. And the size of I prime is never larger than f of p for some function f. So we call f of p the kernel size. And if f is a polynomial function, then we call this whole algorithm a polynomial kernelization algorithm. So such an polynomial kernelization algorithm highly depends on the parameter we're looking at. And in this case, we want to look at longest path modulators. I first explain what is a longest path modulator. So in this graph, we call a set gamma, subset of the vertices, a d longest path modulator for some constant value of d. if the graph G minus gamma does not contain a path of length D plus 1. So in this example over here, we have a 3 longest path modulator, this set over here. And now we can easily see that this set is a 3 longest path modulator by just removing the vertices of gamma from the graph. And now we see there is no path of length 4 in the remaining graph, only paths of length at most 3. But note that this does not necessarily bound the size of the connected components in V minus gamma. So, for example, here this center vertex can have as arbitrary many other neighbors, and still this component would only have a longest path of length 3. So this set might look obscure at first, so these longest path modulators, but actually they are a generalization of a very famous parameter. So for the d equals 1, so the 1 longest path modulators are exactly the vertex covers. And a vertex cover, or the size of the smallest vertex cover, named the vertex cover number, is a very famous parameter used in many parameterized algorithms. So what we are looking at is not longest path modulator itself, but kappa d, which denotes the size of the smallest d longest path modulator, and we call this kappa d the d longest path deletion number. And we are now able to show that all colored cut games admit polynomial kernelization algorithms of size at most kappa d squared times k to the d plus 1, where k denotes the total attacker budget, so the sum over all A1 to AI. So let's move on to the kernelization algorithm. So we assume that we have for a constant value of d our d longest path modulator gamma, and we want to compute for each pair of distinct vertices of gamma, AB, the color sets of direct AB path in this graph. And with direct, I mean AB paths that do not contain a third vertex of gamma. So, for example, this red-gray path over here would be a direct path from S to V1. But on the other hand, the path S, this red-gray green-gray path over here from S to V2 would not be a direct path, since we have the third vertex of gamma, namely V1 in this path.
To compute such a set AAB, we can just simply remove all the remaining vertices of gamma besides A and B from the graph and just look at V minus gamma and these two vertices A and B. Here in an example, let's start with S and V1. If we want to compute the set A S V1, we can remove V2 and T from the graph and just compute all the color sets of S V1 paths. So here in this example, we see it's red and a gray path, blue, green, gray, green path, and a purple, green path. And we can compute all these paths efficiently since gamma is the longest path modulator. So each of these paths and each of the color sets in these collections has a size at most d plus 1. And since d is a constant, this can be done in polynomial time. So next we compute the set ASV2. We compute all the SV2 paths in this graph and compute their color sets, and so on until we reach the last of the gamma choose too many of these collections.
So we have computed these sets A, AB for distinct vertices A, B, and gamma. And also these are collections of color sets. And a color set is a AB cut in the graph containing only the vertices AB and V minus gamma. If and only if this color set is a hitting set for this collection AAB. So there is this close relation I mentioned earlier between colored ST cuts and hitting sets, or colored cuts and hitting sets. And what we want to do now is we want to somehow reduce the size of AAB in the following way, that we obtain a smaller collection of color sets, such that these A prime AB and AAB share the same hitting sets of size at most K. And since the attacker can only choose K colors, he can never obtain a colored ST cut with more than K colors, or a colored AB cut in this case, with more than K colors. So as long as these two collections share the same hitting sets of the size at most K, we don't lose any information for this game. And well, what we know what to do is we want to obtain that this new collection of color sets is small in some way. And to this end, note that since gamma is a d longest path modulator, each of these color sets in AAB has at most, or contains at most, d+1 colors.
And with the help of the famous sunflower lemma, together with the use of known reduction rules for the hitting set problem, we are now able to obtain such a smaller set A prime AB with at most O of k to the d+1 many color sets. So both of them share the same hitting sets of size at most k, but this new set, this new collection of color sets, is presumably much smaller.
So now we have all these sets, A prime, SV1, A prime, SV2, and so on, computed for all pairs of distinct vertices of gamma. And now we only have to bound the number of vertices not contained in gamma to obtain our kernelization algorithm bound. And we do it the following way. We remove all the vertices of V minus gamma. And now for each of the color sets in A prime SV1, we add a new path between S and V1 containing exactly these colors. So now we for this collection A prime SV1, we obtain these new paths in between. And we also do this for all the other distinct pairs of vertices of gamma. And so also for I prime V2T. And in our paper, we showed that this new instance is equivalent to the original instance. So the defender has a winning strategy in this instance, if and only if he had a winning strategy in the original instance. So the only thing remaining is we have to show the size bound of the kernel. So the size of this new instance is at most gamma choose 2, or gamma squared, many of these collection of color sets. Each of these collection has size at most O of k to the d+1, and each of the color sets in each of these collection has size at most d+1. So in total, this whole instance size is bounded by O of gamma squared times k to the d+1. So let's end with a small conclusion. In our paper, we introduced the colored cut games and analyzed their complexity. We were able to obtain non-trivial polynomial kernelization algorithms for all of them, so also for the colored ST cut and the labeled path problem. And this is pretty nice, since for both of these problems, only few polynomial kernelization algorithms were known so far. Also, we were able to obtain these kernelization algorithms by combining the attacker budget and the graph parameters. So it would be interesting for the future if it is possible to obtain positive results by combining the defender budget and structural graph parameters. And also if one can obtain kernelization algorithms for other p-space hard problems. Until now, there are only few p-space hard problems for which polynomial kernelization algorithms are known. Well, that's all for now. Thanks for your attention. Hope you enjoyed.